All right, algebra, getting close to being all done with chapter 13. Woo-hoo! Hallie's cheering for you. We have 13.7 and then 13.8, and then we're done with this textbook. Y'all, that's nuts. Okay, so let's get started. 13.7, applying rational equations, okay? Yay! Everyone, 3 cheers for motion problems. If you could see me right now, you would see that I'm literally giving you spirit fingers because I know how excited you guys get for motion problems. Rate times time equals distance, and you can already see that there is a chart on this page, and some of you are so mad right now, and I am giddy because I love this stuff. So we're just going to dive right in, all right? I'm reading the actual problem straight from your book. I did not write the entire thing down. I just wrote down key information. You're probably going to want to have your textbook out, and I need to double check something really quick. Sorry, before I keep going. Okay, good. I did. All right. So anyways, back to this. Here's the problem. Troy and Philip decided to spend the day canoeing on a river with a 3-mile-an-hour current. Okay, so the river is traveling at 3 miles an hour. They began paddling upriver at 9 a.m. So when you're paddling upriver, you're fighting the current, right? After stopping on an island for an hour to eat lunch, there's an island in the middle of this river. Fascinating. They paddled back down the river. So when they're paddling back down the river, the current is pushing them along. It is helping them. And they arrived back at their starting point at 3 p.m. If they typically paddle at 5 miles an hour in still water, how far upriver did they travel? And when did they stop for lunch? So D is going to be the distance that they traveled up and down the river, okay? Because they traveled up and then they came back, all right? So the distance that they went one way is going to be equal to the distance that they went another way. So our distance in this case is just D, all right? Now, we know there's a 3-mile-an-hour current that they're working with, okay? We know that they were back at their start at 3 p.m. after starting at 9 a.m. Okay, so they were gone for a total of how long? They were gone for a total of 6 hours, all right? Gone for a total of 6 hours. And somewhere in the midst of that, they took a 1-hour break, okay? They took a 1-hour break. When they're paddling without the help or the hindrance of a current, they are paddling at 5 miles per hour, okay? So when they're going upstream, they are fighting the current. So we take their paddling with nothing, okay, paddling just in still water is 5 miles an hour. And we subtract that current, remember, because it's going to slow them down to figure out how fast they're actually traveling when they're going upstream. So they're going 5 minus 3 is equal to 2. So their rate going upstream is 2. Their rate going downstream, they're going faster. So we add the speed of the current to their normal rate, and they're traveling 8 miles an hour as they're going down. Now, their time, okay? How do we figure out this t in the middle here? All right, we need to determine the expression for the time by solving. What is wrong with my pen? Rate times time is equal to distance, okay? How do we solve for time? T is equal to distance over rate. So what we're going to do is we're going to replace t with d over 2 and d over 8. Now we have everything in reference to just one variable, and we could actually solve, okay? So now, how are we going to do this? Well, we know that the time that they actually were paddling, okay? How long were they actually paddling? How long were they actually canoeing? Don't say 6 hours. They were gone for 6 hours, but they took a 1-hour break. So the total time that they were actually paddling was 5 hours. So the time upstream plus the time downstream is equal to 5 hours, okay? So time upstream is d over 2. Time downstream is d over 8, and that is equal to 5, okay? Multiply everything by the LCD. That's going to be 8, okay? What that's going to do here is we're going to end up with 4D plus D, 8 times D over 8, is equal to 5 times 8, 40. What is up with my pen? So that's 5D is equal to 40. So D is equal to 8. So D is up and D is down, okay? So that means 8 miles upriver, okay? Or 8 miles downriver. That's how far they traveled. The other question was, when did they stop for lunch? So what we need to figure out is D over 2 is equal to 8 over 2 is equal to 4 hours upriver. They left at 9 a.m. So if they stopped for lunch after paddling upriver for 4 hours, that means they stopped for lunch at 1 o'clock. Stopped for lunch at 1, okay? So they traveled 8 miles each way, and they stopped for lunch at 1 o'clock. Example number 2, okay? When Lisa flies home for Christmas, her flight time is 12 and a half hours shorter than the time it would take her to drive the 780 miles. If the plane's average speed is 6 times the average speed of the car, that means the plane is 6 times faster than the speed of the car, find both speeds, all right? So what we're going to do, R is the speed of the car, and we know that the plane travels 6 times faster than the car, so 6R is the speed of the plane. So let's start filling in our chart. R is the speed of the car. 6R is the rate of the plane, okay? Distance, we're told it's 780 miles. So distance for both of these is 780. Now again, our typical formula is R times D is equal to T. We need to get that T value in there, all right? We need to figure out what T is. So divide both sides by R. T is going to be D over R. So looking at what we have, the time by car is going to be 780 over R, and the time by the plane is going to be 780 over 6R, all right, over 6R. Now, what do we actually know here? What do we know? Well, we know that it's 12 and a half hours longer for her to drive than it is for her to fly, okay? So that means her car time, or time car, I should have put that, actually, let me just do that. The time, or T, in the car is equal to the time of the plane plus 12 and a half hours. Okay, let's start plugging in some information that we have here. Time on the plane is 780 over 6R, that's our T, plus 12.5 hours. I'm going to go ahead and I'm going to put that into a fraction because I have fractions happening here. 12.5 is 25 over 2. That's equal to the time in the car, which by our chart, okay, is 780 over R. Okay, what am I going to multiply everything by? I'm going to multiply both sides by 6R. What that's going to do in my first expression, 6R times 780 over 6R, my 6R's are going to cancel and I'm left with 780. 6R times 25 over 2, okay, is going to give me 6 times 25, okay, 6 times 25 is 150 over 2. So 150 divided by 2 is 75, and then I still have that R. So 75R, and that should be a plus, not an equal. So 780 plus 75R is equal to, And then what's happening on the right side? My R's are going to cancel, and we're going to have 780 times 6, which is 4,680. Subtract 780, and 75R is equal to 3,900. Divide both sides by 75, and the rate is 52 miles per hour. Now, R by itself is the speed of the car. So this is the car speed. The plane speed is 6R, so that's 6 times 52 miles an hour, which is 312 miles per hour. That is the plane speed. Okay. Now, moving on to example number 3. Okay. Back up. Let me read a couple paragraphs just above this example. A manager's ability to accurately predict the amount of time needed for his associates or his employees to complete a task allows him to maximize their efficiency without burdening them with unrealistic expectations. The work problems in this section can help you analyze some of the everyday jobs in which you may be involved. Rates of work will typically be determined from information in the problem. If Joe completes a project in 1 hour, so if he does one project, if he completes a project in 8 hours, if he does one project in 8 hours, that would be one project over 8 hours, okay? Then he completed 1/8 of the project per hour, right? That's the rate at which he's working at, all right? Keep that in the back of your mind as we move through this example. Example number 3 says, the yearbook advisor knows that Allison can proofread a chapter in 60 minutes. Sean can proofread a chapter in 75 minutes. How long will it take them to proofread other similar chapters if they work together? So we're going to let M equal the minutes that they are working, or the minutes that it should take if they work together. All right, so the time that it takes for Allison to do the task is 60 minutes. The time that it takes Sean is 75 minutes. The time that it takes them together is what we don't know. So that's our variable. So that's M. Okay, what's Allison's rate of work? Allison's rate of work is 1 chapter per every 60 minutes. Okay, so 1 chapter over 60 minutes is Allison. It takes Sean 75 minutes to do 1 chapter, so he can do 1 chapter per 75 minutes. Then together, they're going to be able to do 1 chapter per M minutes, where M is what we are trying to solve, okay? Now, 1 over 60, Allison's rate plus Sean's rate will give us the rate that they work together, 1 over M. Now we need to solve this for M. We're going to multiply everything by M, okay? We're also going to multiply by 300. Now, you wouldn't have to multiply by 300. 300 helps you. Why? Because it's going to help us clear our fractions, and that's what we want. So 300M times 1 over 60, 300 divided by 60 is 5. So 5M becomes our first term. 300M times 1 over 75, 300 divided by 75 is 4. So that is 4M is equal to 300M times 1 over M is equal to 300. 9M is equal to 300. Divide both sides by 9. And M is 300 divided by 9, which is 33 1/3 minutes. So together, it will take Allison and Sean 33 1/3 minutes to work together. Now what you want to do when you have an answer like this to a story problem is say, take the moment to say, does this answer make sense? Okay? Yes, it does. Okay, it should be less than Allison. It should be less than Sean. Okay? And excuse me. So we know it's less, it looks about reasonable, all right? What I want you to notice also is that if we were to figure out what the average is between 60 and 75 minutes, it would not equal this, okay? So you cannot just say, oh, I'm just gonna take the average, okay? You've got to work through the problems using the method that we just talked about, all right? Example number 4 is a similar type of problem. Mr. Matthews owns a landscaping company and schedules the jobs for his company. He can complete the weekly maintenance for one of his clients in 10 hours by himself, okay? So if Mr. Matthews is working all alone, it's going to take him 10 hours. Or he can complete the task in 4 hours with his assistant, Ned, okay? With his assistant, Ned. So together, it takes them 4 hours. How long should he schedule for Ned to complete the job by himself? So we want to know, how long would it take Ned by himself? It takes Mr. Matthews 10 hours by himself. It takes Ned and Mr. Matthews together 4 hours. So what's the rate of work? Mr. Matthews can do one job in 10 hours. Together, Ned and Mr. Matthews can do one job in 4 hours. Ned, what we want to figure out, can do one job in H hours. Okay, now, Mr. Matthews' rate of work plus the rate of work with him and Ned is equal to the rate of work if they do them together. What are we going to multiply everything by? Multiply both sides by 20h this time to clear our fractions, okay? That's going to clear the h's. It's also going to clear the 10 and the 4 because 20 is the least common multiple of 10 and 4, okay? So 20h times 1 over 10, 20 divided by 10 is 2, and we're left with an h. 20h times 1 over h, so that's just 20 times 1, and we're going to end up with h divided by h. So that's just 2h plus 20 is equal to, and on the right side we just have 1/4 times 20, so that is equal to 5. Now, 5h, forgot about that h right there, okay? We're going to subtract 2h from both sides, and 20 is equal to 3h. Divide both sides by 3, and we get 6 2/3 hour. So h is equal to 6 2/3 hour. So it takes Ned 6 2/3 of an hour to do the work. So Ned by himself is more efficient than Mr. Matthews by himself. But no matter what, one person by themselves is not going to be as efficient as two people together. So Ned is a little bit more efficient than Mr. Matthews, but it would definitely be better for them to do the work together. Okay? And that's how we work through the problems in this section, or in this section. You guys make charts or tables, whatever you want to call them. They will help you. I only assigned, I think, 15 problems for this assignment because I want you to be diligent and take the time to write out a chart for every single problem. If I do not see a chart for every single problem, I will not grade your work. The end.